Welcome back. So, the theme of this couple of weeks is thinking about how to take states and evolve them through time, of course, by finding out what the eigenstates of the Hamiltonian are, and then using the time evolution operator to move those states forward. Now, a big topic that comes up right now is the idea of doing what's called spin precession, which is to see how the different components of the spin vector might evolve through time if I put them in some external magnetic field such that the different states of spin have different energies. So I want to walk through kind of a couple of examples quickly, just so that we can talk about how these equations actually get written down. We can talk about how we can do some of these interesting calculations. So for this, I'm going to take kind of the standard setup where I'm going to calculate the energy of a magnetic dipole moment in an external magnetic field using the equation E is minus mu dot B. In a moment, this will become our Hamiltonian. And plugging in the expression for, if I say that the magnetic field is only going to be in the z direction, then I can plug in my expression for mu in terms of s, and I can do the dot product out. And I get this nice little compact form about what the energy of the state is going to look like. And now it's clearly an operator, right? So now it's really looking like we should just call it the Hamiltonian and call it H instead of E. But I am going to do a quick simplification just so that way I don't have to write down as many things on the next couple of slides. I'm going to replace these unknown factors, right? The G, the Q, the M, the B naught. I'm just going to call that omega naught for now, right? Someday, you might want to plug it in, you might want to find out what these numbers actually are, but that day is not today, right? And because I don't want to get lost in saying all of these things all the time, I'm just going to go ahead and call that thing omega naught. So if I have this Hamiltonian, what I have to do is I have to use that Hamiltonian to generate the time evolution operator, which means plugging in what I had on the previous slide, right, into the expression for the time evolution operator, where I'm going to allow the state to go forward by some amount of time that I'm going to call delta t. Now, often people will just write t here, which is actually totally fine as long as you remember that you're starting at 0, right? And then tf minus ti, if ti is 0, is just given by tf, which you might as well call t. But I do want to remind us that the time evolution operator is something that really gives us sort of some jump forward in time, right? And that's why I'm going to keep around the delta t a little bit longer than your book does. So I'm going to do some examples with this explicitly, and in order to do that, I need to come up with some representation of SU2. And so I'm going to go to a spin 1 system, so a 3-dimensional representation. And if I have that, I can sort of quickly write down the SZ operator in its own basis, right? I'm going to do it the easy way. And then plug that SZ into the expression for the time evolution operator, and I get out a nice diagonal matrix where the entries, of course, along the diagonal are the eigenvalues of the time evolution operator. And you can see now why the omega naught makes it sort of a nice, pretty little thing to write down, right? So e to the minus I omega naught times delta t is what really appears in that first entry, and I would be going against things that I find very interesting by not mentioning, right? E to the I omega t is something that we've seen before. Anyway, so I'm going to do the first example by saying I'm gonna allow my state to evolve, but my initial state is just going to be a beam that comes out of a Stern-Gulick experiment in the z direction, right? So I start with a plus z state, and I'm going to allow that state to evolve through time, which means applying the time evolution operator to that 1, 0, 0 state. And what I get out is this thing. Let me circle it in green here, right? What I get out is a time-dependent probability amplitude. And you'll note, right, this is always normalized because the time evolution operator is unitary. But the other entries are 0, right? So it's sort of trivially normalized because all I have is a probability amplitude that's a complex exponential. And this is actually one of those situations where, of course, well, if I take the norm with itself, I'm just going to get 1, right? Like it seems pretty straightforward. But what's hidden in that phase, right, that time-dependent phase that goes along with the probability amplitude in the first entry, really is what's going to allow us to do all sorts of neat interference and quantum effects later on. But here it doesn't seem to, just looking at it, it doesn't seem to play too huge of a role. So, but to continue with the calculation, just so that we can see how these things are done. Now that I know what the time-dependent state looks like, I can ask questions like, what's the expectation value of measuring this state through another SZ apparatus, right? So I can take the expectation value of the full time-dependent state, which means taking my ket, turning it into a bra, sandwiching an SZ operator in between them. And I can do out this matrix multiplication, right? The first one is just going to give me an h bar, and so I get e to the I omega naught delta t 0, 0. I haven't done anything with that yet. And then I have an h bar e to the I omega naught. I dropped a minus sign here. Sorry, e to the minus I omega naught delta t 0, 0. And of course, e to the I omega naught delta t times e to the minus I omega naught delta t is just 1. And so I get out that this is h bar, and this is a constant, right? And so when I found out that all of this stuff we've been doing with passing a state from one apparatus to another, I haven't been lying to you that much, right? Because it turns out that if I'm in this state, it's actually not going to change the expectation value of measuring. I should say it's not going to change the expectation value of the state, right? It's still going to be expected to have a measurement of h bar. And I can do some slightly harder expectation values, right? So take this same time-dependent state, and now let's measure, well, what's the expectation value in the SX direction? Well, again, it's matrix multiplication. I'm not doing anything with the first vector yet. I'll do my matrix multiplication on the second vector. Well, in this case, 0, 0, 0 gives me a 0 up here. And now I'm left with an h bar over the square root of 2. By the way, I looked up the SX operator, right? I don't have to rederive it here. But h bar over 2 e to the minus I omega naught times delta t. Oh, and I forgot my delta t there. And then a 0. And it's 0, right? Also something that's not time dependent, right? It's a sort of less interesting thing that's not time dependent, but it's something that's not time dependent, right? And this is because I'm in a pure state of the SC operator, right? And I'm allowing the states to evolve, right? And the Hamiltonian commutes with the SC operator, and so things aren't really getting mixed up, right? Of course, I can break this, right? Because if my Hamiltonian shares eigenstates with the SZ operator, then it stands to reason that I can probably mess things up if I have a state that's not a pure state of the SC operator. And you can probably guess what I'm going to do. I'm going to start in a state of the plus, I'm going to start in the plus x state. So I'm going to start in an eigenstate of the SX operator, right? Which has which I can write in the SZ basis, right? So I can break it up into the eigenstates of the SZ operator. But hopefully this is going to give me something more interesting, right? Because I'm creating something that is not an eigenstate automatically of the Hamiltonian, right? It's a superposition of eigenstates of the Hamiltonian. So when I apply the time evolution operator to this state, what I get out is that I have e to the minus I omega naught times delta t, over 2, right, because I have that 1/2 on the ket. And then the second entry, nothing happens to it, which is probably, well, we'll talk about that later. And then an e to the I omega naught delta t over 2 on the bottom, right? And so now I have stuff all through my matrix, and that makes me kind of excited when I go to calculate expectation values of this, because now there's an opportunity maybe for these terms to conspire with each other and give me something interesting. I'm not going to do all of the expectation values, but I'm going to do one of them, right? I'll do what's the expected value of Sx given this time-dependent state. And I've written out some of the algebra here. Actually, on the top line, I've already written out what the time-dependent state looks like in the SC basis with all of the beautiful delta t's there, and then what the expectation value looks like once I write it out in the SC basis. Okay, so let's do it, right? I'm not going to do anything with the first vector, e to the I omega naught delta t over 2, 1 over the square root of 2, and e to the minus I omega naught delta t over 2 is the third entry. Now, when I do out this ket, I actually have to do a bunch of matrix multiplications, right? So the top one is 0 times the exponential plus h bar over the square root of 2 times 1 over the square root of 2 gives me a 1/2. The next one, this is cool. Okay, right? So I have, and I should say there's an h bar. Oh, there's an h bar there. H bar over 2. Now the second one, I'm going to have an e to the minus I omega naught delta t, right? And then it's going to be divided by the square root of 2, divided by 2, and multiplied by h bar. So I have h bar over 2 root 2 times e to the minus I omega naught delta t, right? That comes from the first one. And then the second one is going to give me the same thing, right? But it's going to not have the positive sign, right? It's going to have it's not going to have the negative sign. It's just going to have the positive sign. So I have an e to the I omega naught delta t. And then let me just quickly do the bottom one. So this is h bar over 2. Now, before I go on with this, right, I just want to take a moment and think about, right, we've seen what happens when I have an e to the I omega t plus an e to the minus I omega t, right? That is a cosine, right? I mean, there's a factor of 2, but luckily I have an extra factor of 2 in the denominator that I can suck up into it. But cosine omega naught t is equal to e to the I omega naught, delta t, plus e to the minus I omega naught delta t over 2, right? And so I can see that I'm getting these fun transcendental functions out of doing this matrix multiplication, right? So let me just finish this, right? Because it's going to be, okay. All right, so I have e to the, it's going to be beautiful. Okay, so I have e to the I omega naught delta t over 2. Then that's going to be multiplied by h bar over 2, right? That's the first one. I'm going to skip, well, no, I won't skip the second one. I'll just write it over here. I have plus h bar over 2, right, because the square root of 2's, times the cosine of omega naught t, right? And then the third term gives me a plus e to the minus I omega naught times delta t over 2. Huh. Look what we found again, right? I mean, this is yet another cosine, right? And even the 2's work out, and then I have an h bar over 2, and so I get something like h bar times cosine of omega naught times delta t. Apologize for missing these deltas, but what you can see is that now the expectation value of the x component, right? No, sorry. The expectation value of the x component of the spin is going to oscillate, right? And it's going to oscillate, around, well, basically it's going to oscillate around the z-axis, right? So that the x value gets bigger and then 0 and then smaller and then 0 and then bigger, right? It's going to oscillate backwards. And I bet if we calculated the expectation value of sy, right, we would probably get something like a sine out of it, right? And anyway, I don't know. This is fun, right? We see why that x component is going to, or we can see why the spin vector, we can visualize it as spinning around the z-axis the way that we did when we studied just regular magnetic dipoles in the presence of a magnetic field. Okay? And, the units work out and the transcendental function is fun, and it's nice when algebra makes us feel good. Okay, anyway, So about this, right? Why, I want you to think about these derivations. I want you to look at these steps and not be so intimidated by the fact that you have to do all of this matrix multiplication now. But there is a lot of algebra associated with it, and there are trig identities, and there are things that we have to deconstruct and then reconstruct. But as long as you write down your eigenstates, right? That is, write down all of your states in the Hamiltonian eigenbasis, right? Then it's much easier to deal with the time evolution operator. And if it's easier to deal with the time evolution operator, then it's generally easier to do. All of these matrix algebra. Okay, so don't worry about it. It's just algebra.